Hello everyone. So in this video, I'm going to go over some of the problems in the study guide, and this is the final exam study guide. Now let's quickly look at number 6. Now in number 6, we've got a popular breakfast company fills their cereal bags with an average 80 ounces of cereal and a standard deviation of 7 ounces. Now, right there in this sentence, we've got an average of 80 ounces, which is the population mean. And it's population mean because there is no sample attached to it. So it's just the general, right? The breakfast company says they fill their cereal bags with an average of 80 ounces. So this is population mean and a standard deviation of 7 ounces. Now, this standard deviation also comes from the population. Again, it has no sample, random sample, whatever attached to it. So we've got population mean, we've got a population standard deviation. We sample 36 bags. Now we have the sample and find the average weight of those cereal bags to be 77 ounces. So right there, we know that this 77 ounces is an average or a sample average or a sample mean. So the question is, we should compute the 95% confidence interval for the mean based on our sample. So we're going to find the 95% confidence interval for the mean. First of all, remember we did this in class. You have to know what kind of confidence interval am I trying to find? Confidence interval for the mean. So since we have the population standard deviation, we are going to be using the Z distribution formula for confidence interval, Z distribution mean. And you're going to find this on the formula sheet, which is going to be given to you on the exam. So this is going to be the formula for confidence interval for the mean using the Z. That's the formula. So X bar plus or minus the critical value of Z times the population standard deviation divided by the square root of n. Now, let's plug our numbers in. The sample mean is 77 plus or minus. Our Z, remember, you could get the Z from the chart. You could get the Z from the chart. In the other video, I showed you where to find it. So you go to your Z table, and then you have the chart, that little chart there in the left corner below, or yeah, right at the bottom, left corner, right at the bottom. So your Z for 95% is 1.96 times a standard deviation of 7 divided by the square root of 36. So the next thing we've got to do is to go to our calculator and then calculate for this. Now we also know that this part here is a margin of error. Oops. Let me do this again. This part here is our margin of error. So we find our margin of error and then we add it to the sample mean and we subtract it from the sample mean. So if we decide to go to the calculator, so we've got 7 divided by square root of 36. Square root of 36 is 6, but let's say we didn't know that. Oops, let me do this again. So 7 divided by 6, or you do the square root of 36. And that gives you a 6. So 7 divided by square root of 36 is 1.6666. I'm not going to round. Now remember that at this point, our margin of error was that, but I did this part. So I've got to multiply it by the 1.96. So times 1.96. Oops. 1.96. And then I've got 2.287. And there's a plus or minus. Now I bring the sample mean. Then my two numbers, the lower and the upper is going to be 79.287. And then the lower is going to be 2.287, 74.713. And that is it for my confidence interval for the mean for problem 6. Now, in problem 7, we have a similar problem. And I think I already went over that in class, so I'm going to skip that. And then I'm quickly going to go to number 10. Number 10. Now, 8, 9, 10 are all, looking for the same thing. We are finding the sample size or the minimum sample size required. So I'm going to go to 10 just because we did some of these already. So in number 10, if we want to have a 99% confidence interval about the mean to have a margin of error of 10, what will the minimum sample size required be if the population standard deviation is 25? Here again, you've got to go to your formula sheet, and then you're going to go look for the minimum sample size formula. And remember, this is for the mean. This is for the mean. And here we already have this population standard deviation, which is good, so you know you're using the Z. Now, when you go to the minimum sample size formula, and this is for the mean, so you're going to have N equals your Z, C times your standard deviation divided by the margin of error, and then a squared on it, a squared on it. Do not forget the squared. So this would give us a Z of 99% is 2.58. And again, you could get that from the table. So 2.58 times a standard deviation of 25 divided by 10, which is our margin of error, all squared. So now you go to your calculator. Remember PEMDAS, you've got to solve what is in the parentheses first. 2.58 times 25 divided by 10. That gives me 6.45. And then you put the squared. We've got 41.6025. And remember what we said in class. When you're solving for n, you always, because sample size, you're looking at people usually, or maybe machines. So it's always going to be something whole, or it's going to be a person. And you're never going to get a point something of a person, right? So even if it's at 41.32, just round up, add 1 to the whole number. So you're going to here we're going to get 42. So you always want to add 1 because you don't want to get a point 0.6 of a person or a point 0.3 of a person or something. But this is what we know. If it's 41.235, you know that it's more than 41. So you're going to add 1 to it, and then it turns to 42. So here, our sample size is going to be 42. All right. Now, 11 and 12, uh, yep, 11 and 12, that I'm not going to go over that. 11, what does the confidence interval tell us? Remember, the answers are at the back, so you could always go and then refer to it. What are the appropriate conclusions? Yeah, I'm going to skip that too. 13. What set of hypotheses are used for the following? a left-tailed hypothesis for the mean. So here, a left-tailed hypothesis, remember that for a left-tailed hypothesis, the left-tailed really is got from the alternative hypothesis or the alternate hypothesis. So H1 mu is less than X, like that. You seen it? That's a left-tailed hypothesis. Now, if it's a right-tailed, the null is going to be the same. The H1 is going to change. Right-tailed is greater than X. And then a two-tailed, this is going to be a not equal. And remember, the X is just a variable. It's a number, so it doesn't matter. You could do Y, you could do mu 0 or mu X. It's just a variable. Left-tailed hypothesis test for the proportion. So everything is going to be the same, only that because it's proportion, the symbol is going to change from mu to P. And then H1 for left-tailed for P is less than X, like that. All right. I'm going to quickly go to number 19. In 19, it is claimed that the best golfers in the world make 75 of their putts within 10 feet of the hole. A random sample of 95 putts was taken and found that 76 of them were made. Do we have enough evidence at the alpha equals 0.05 level that this value is larger than 75%? So here we want to run a hypothesis test. The first step is always to make sure you set up your hypothesis. So this is B equals 75%. And this is P because it's percentage. Remember, proportion or P is always a fraction, decimal, or percentage. And then it says, what are we testing for? Let's see. Do we have enough evidence that at the alpha level of 0.05, this value is larger than 75? Okay, so larger than 75%. Now, step 2 is to find your test statistic. And here, because this is a proportion problem, we're going to go to the test statistic formulas, and that is going to be in the formula sheet. And we find Z, and that is going to be P hat, which is the sample proportion, minus P divided by EQ over N, like that. So we've got to plug in our values. Now, for P, remember there are two P's. For the P, is going to be this, right? Because it's right here. P is 0.75. But what about P hat? P hat is the sample proportion or the estimated proportion. Now, proportion is always a fraction, remember that, or a decimal. So a sample proportion, we're going to get that by going to where it talks about the sample. So a random sample of 95 putts was taken and found that 76 of them. So 76 out of 95. So our P hat is going to be 76 out of a 95. And you put that into a calculator if you want to, and that should give you 80% or 0.8. So P hat is 0.8. P is 0.75. Now Q, this is not Q hat. This is Q. So that's going to be 1 minus P. And Q, that is also on the formula sheet. So 1 minus 0.75, that gives you 0.25. Oh, so we've got our Q. And then our N, the N is going to be the 95. The 95. So we put this in, we have, or plug the numbers in, we have 0.8 minus 0.75 over the square root. P is 0.75. Q is 0.25 divided by N, which is 95. Now, you've got to go to the calculator. Now here, you've got to do the top. That is 0.8 minus 0.75 first. That is 0.05. That's what you get. So you write that down, 0.05. And then you go to the bottom. Now, for the bottom, you have to do what is under the square root first, and everything at the bottom is under the square root, or the square root affects all of it. So you do everything first, 0.75 times 0.25 divided by 95, and that gives you 0.001973684211. And then you put a square root on that, and that gives you 0.04443. So for the top, I had 0.05 divided by what I got for the bottom, 0.04443. And that should give us 1.125. Now, because this is a Z statistic, you want to keep it, or this is a Z value, you want to keep it at 2 decimal places. So instead of saying 1.125, you say 1.13, 1.13, 1.13. So my Z is 1.13. Now, the next thing to do is to find your p-value. So you go to your Z chart, and then you're going to find your p-value. But remember, we are running this test. Look at the alternate hypothesis. We are saying that P is greater than 0.75, which is a right-tailed test, which means that you're going to do some subtractions. You're going to subtract from 1 when you go to the left. So 1.13, if I go to my Z chart, so let me get that going. All right, so I'm going for 1.13. So here I'm at 1.1. And then on top here, I've got 0. And then this is what I want, 0.03. Then I go to 1.1. Oh, look at that. I've got 0.8708. But we do know that what we are looking at is a right-tailed. The table would always give us the area to the left. So this part is 0.8708. Now, this is what we're trying to find. So you're going to do 1 minus 0.8708, and that gives you 0.1292. 0.1292. Now, the next step is to compare the p-value to the alpha and then make your conclusions. Now, if our p-value from here is 0.1292 is greater than 0.05, which is alpha value. So P is greater. So we fail to reject. Fail to reject. HO. We fail to reject the null hypothesis. And what was the null hypothesis? It says P is equal to 0.75. So we fail to reject. So we say this is correct. So we do not have evidence that, let me go back to the problem so that I read it in the right way. So we do not have enough evidence at the alpha 0.05 level that the number of puts is greater than 75%. And that's it. Okay. All right. Now with 21 to 24, we did this in class. So I'm just going to do one of these and then move on. So using the student's T distribution, find the critical T value for a 90% confidence interval with a samples when the sample size is 18. Now, this is a T distribution problem. When sample size is 18, degrees of freedom is n minus 1, which is 17. And then my confidence level is 90%, which is 0.9 or 0.90. So I go to my chart, the T chart, and then, okay, so this is not what we are doing, but let me just chip this in. This is the critical Z values, right? Where to find the critical Z values. All right. That's just by the way. Let's go to the T chart. Yep. So degrees of freedom is 17, and then our C value is 0.9. So you bring it down, 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 down to 17. So C, remember you're looking at C, 0.9, which is 90%, and then that is a 17, so 1.740, and that's it. All right, so that's how you deal with these. All right. Now let's quickly look at one example from 29. If we run a hypothesis test for the mean using the T distribution, what would be the critical T value used for the following test types? Sample size and alpha value. Now look at the first one. Left-tailed, n equals 30, alpha equals 0.05. Now with T distribution again, remember you're doing degrees of freedom, which is n minus 1. Degrees of freedom is n minus 1. So if n is 30, degrees of freedom is 29. Now this is left-tailed, and we are supposed to find a critical T value. Now I'm going to go to the chart real quick because that is very important. Now if you go to the chart, on the left of the chart, you would see that here we have a left-tailed curve, and it tells us that the T is always going to be negative. So if I go to the chart and then find degrees of freedom is 29, I'm going to scroll down. But because this is left-tailed, I'm going to go to, this time around, I'm not going to use the C. I'm going to go to a one-tail area and then find the alpha, which was 0.05. Let me check again. Yep, 0.05. So 0.05 is right here for one-tailed. And then I go down and down and down and down to 29. Down and down and down and down and down and down to 29. And then, yep, that's going to be right here, 1.699. But because this is left-tailed, it's going to be negative. And we did this in class, so negative 1.699. Now, when it's right-tailed, it's positive. So that you don't need to put a sign on it. When it's two-tailed, it's negative and positive. So plus or minus. when it's two-tailed. And when it's two-tailed, you want to go to the two-tailed area and then find the alpha from here. If it's right-tailed, left-tailed, you're doing one tail. Right-tailed, left-tailed, one tail. And that's it. All right, I'll see you in the next video. Bye.